Hello everyone and welcome to the next video of this series about working on the project of my own functioning GLaDOS miniature. Last time I implemented the voice recognition to control the program with my voice. This video is about how to get the program to use sound to respond to commands. This feature is essential and was also present in the old program like the voice recognition. Having both voice recognition and sound output will enable me to have proper dialogues with the program. As usual, before I jump into the design, I first want to quickly cover the requirements. Obviously, I will take the previous program version with the voice recognition as given. The second requirement is some form of text-to-speech service that will provide me with the required sound files. More on that in a bit. The third requirement is to narrow down which words should be possible to be output from the program. This will also be covered in the next chapter. That was it for the requirements. Let's move on to the design of concept. Since the previous work on the program left me with the required actions already being sent to the sound manager, implementing the sound output will not be that difficult. We can already see the advantage of planning the program in detail before actually implementing it. In the old program, I used a set of sound files that contained a single word each. The program extracted the individual words from a given string and played the corresponding sound files in sequence. This approach was developed by thinking of the alternatives. One alternative is to use online text-to-speech services to generate the sound files on demand, but I would run in trouble if the service goes offline. This is not according to the whole idea of this project, which is to be independent of other services at runtime and to not share data with other services online. Another alternative is to generate each possible combination of words in their own sound file and just play this single sound file as a sound. This is not a good way since it would take up a great amount of storage and each new sentence would need to be added individually. This led me to the conclusion of storing each word in its own file and playing them in sequence. Therefore, this approach will be used in this version of the program too. While it sounds easy to just split a sentence into the individual words, care must be taken when dealing with numbers. This is the same problem as one of the alternatives described just now, where each combination would be stored in a new file. This led me to an algorithm that converts any given real number between 0 and plus and minus 1 decillion, which is 1 times 10 to the power of 33. Floating point numbers work too, by the way. This algorithm was developed by myself and is probably not really optimized, but it does it for me. Let me explain how the algorithm works. After creating integer and floating point numbers from the given number string and checking if the number is 0, it is checked if the number is less than 0. If true, the return string is appended by the word minus, and floating point numbers are multiplied by -1. The next step is to cast the integer number back to a string to be able to loop over individual digits more easily. The integer number is used to determine how many triplets are in a given number string. A triplet is a set of 3 digits in any given number. Specifically 3, because that is the way our numbering system in base 10 works. Here's an example. This number is 9,384,145, meaning it has 7 digits. We naturally know that this number contains the word 9,384,145. If we take a closer look to how these words are structured, there's always some group of 3 digits appended by their decimal place. For example, the 145 is the first triplet and has no additional decimal place. The next triplet, 384,000, is the next triplet with a decimal place of 1,000. The last triplet is the 9 million. This still counts as a triplet, even though it only contains 1 digit. This is how I found a reliable way to split a word into structures that I can pass correctly into words. With the number of triplets in a given number string known, the algorithm then loops over every triplet and extracts it from the number string. The triplets are then converted from numbers to text. The conversion is a bit difficult, but the main strategy is to have multiple arrays that contain all positive integers under 20, all teens names like 30 or 80, and all decimal steps like 1000, million, septillion or decillion. These arrays are accessed by taking the single triplet digits and using multiple if statements to find the correct words. The last step is to add the floating point numbers. Here I decided that every digit behind the comma should be named individually without any grouping. One example is the number 3.14. Instead of saying 3.14, the algorithm converts this number to 3.14. The sound output is realized by a new thread that constantly monitors the state of an array blocking queue. This can be seen as a thread-safe queue that will contain sentences that should be played. This thread is designed so that during a shutdown it runs until the queue is empty. This ensures that every sound is played until the program is shut down. The system actually consists of 2 queues that are handled in parallel. The first queue contains the string with words to output. The second queue contains the information in which voice the sound should be played. The path to the sound files is set accordingly. This system enables me to easily add voices, as I just need to add another check for the voice right here, and add the sound files to the resource folder. The voice can then be accessed by every other component in the program. The old program went through the list of words in sequence, meaning that each sound clip was set, opened, played, and closed in sequence. In the new program, this is now split up, which allows faster playback. All sound clips are opened first and then during a loop played and closed in sequence. The state of the thread can be accessed from any other thread. This makes things easy, for example during the voice recognition. Here, the program checks if sound is played before handling any input from the voice recognition, because the sound output is always interpreted as voice input. With the design covered, I also updated the UML, which can be seen here. There were multiple small changes in other components that were not covered last time, but now they are documented here. As usual, you can find all files in my GitHub linked below if you want to get to the specifics. Let's get to implementing the whole thing. The program is implemented as described in the previous chapter and will therefore be skipped here. Instead, I will focus on the more demanding task of creating the sound files. First, I needed to define which words I want to use. I narrowed down the language to English only to make things easier for me. Then, I generated a list of words I used in the old program and in the current terminal prints of the new program. I also added some other words that will likely show up in later versions. The next set of words is a list extracted from the scripts for the first 6 scripted videos from me here on YouTube. The last set of words comes from a GitHub repository I found online. This list was determined by n-gram frequency analysis of the Google's trillion word corpus and is linked below. Keep in mind that the license is for educational and personal use only, so you should probably either use another source or license it for commercial use. Each word list was first filtered to extract names, locations and company names, since I don't plan on using any of them. The 3 lists were then merged to create a master table with all 8,152 words I want to be able to output. Next, I needed to define which voices I want to use. Since I know from my previous videos that I want to use Auto and GLaDOS as the 2 primary voices, I will have to generate a set of sound files for each voice. In case of Auto, it is possible to generate the sound files with the software Repeat After Me in macOS. Check the description for a tutorial video. The software only takes about 25 words at a time due to character limits. This means that I had to divide the master table into smaller tables and process all 334 files manually. This gave me sets of multiple sounds in one file that needed to be split. To avoid manual labor as much as possible, I found out that the audio editing software Audacity can use macros to bulk process audio files. I used several macros to process all files. A first macro to split a labeled audio track into individual sound files, a macro to normalize the sound amplitude and add a bit of reverb, and a macro to cut excess silence from the individual words. While I could not bulk process all files with one macro call, this was still way better than to label, cut, apply and export every word individually. This leaves me with about 8,000 sound files for Auto and roughly 20 hours of work. These files are available on my GitHub, so you don't have to go through the same process. Regarding the voice of GLaDOS, I had the option to stitch together the words from the game files from Portal, but I decided to use the text-to-speech service from 15.ai. Unfortunately, this is down since weeks with no end in sight, so I will just add it in the same way as the voice for Auto when it is up again. In return to the service, I contribute to his Patreon. With the sound files created and the program ready to use, let me show you how it is performing. Generally, I have planned 2 tests. The first test will show how the sound output works in the program by itself. This will be a live demonstration. The second test shows the power of my approach of using so many words individually. I will let Auto read some text for you to get a feeling of how he performs for ordinary speech. This behavior will be the same for GLaDOS.
Initialization of AASMK 1.2 complete. Voice recognition ready. Voice recognition started.
Hello, GLaDOS.
Hello.
Hello, Auto.
Greetings.
Hey, Auto.
Command.
Turn off.
Should the termination of this program commence?
Yes.
Termination of program confirmed. Terminating this program. All components are shut down. Goodbye.
As you can see, the sound output works quite well and Auto still speaks even though the console already said that the program was terminated. The voice recognition sometimes is a bit weird and does not react for some time. Maybe I will be able to fix that at some point. For now it will do though. After the live demonstration, let me show you some text I decided Auto to read.
Captain, you are needed on the bridge. Give me the land. Sir, orders are do not return to Earth. Must follow my directive. Good night, Captain. According to all known laws of aviation, there is no way a bee should be able to fly. Its wings are too small to get its fat little body off the ground. The bee, of course, fly anyway because bees do not care what humans think is impossible. Yellow, black, yellow, black, yellow, black, yellow, black. Oh, black and yellow, let us shake it up a little. Berry breakfast is ready, coming, hang on a second. We are no stranger to love, you know the rules, and so do I. A full commitment is what I am thinking of. You would not get this from any other guy. I just wanna tell you how I am feeling, gotta make you understand, and if you ask me how I am feeling, do not tell me you are too blind to see. Never gonna give you up, never gonna let you down, never gonna run around and desert you. Never gonna make you cry, never gonna say goodbye, never gonna tell a lie and hurt you.
That was it for the tests. Let me move on to the conclusion and outlook for this project. A new engine for sound output was written in Java that can also convert numbers into words. Each voice has its own pathway sound files for each individual word. The words are played in sequence to generate an entire sequence. The tests show that the sound output itself works in the program and that it can output quite different texts at satisfactory quality. Actually, Auto is able to output most words from the script, so I could have also just let him do the talking. The sound output was another core feature of the whole program, and I finally have it reworked. Now I can move on to the next feature that will be the basis for moving the body. The next video of this project will be about the restructure of the communication protocol I wrote myself. The next video will also be about testing the new program on a Raspberry Pi instead of my PC with an IDE. I am really glad how the sound output turned out so far and how much progress I achieved overall in this entire project. Considering that I spent about 40 hours just on the sound output puts my progress into perspective, especially when I only work on my projects in my free time or on the train when commuting to my 40 hours a week job. There will be another video uploaded by me in a relatively short time about another project, so stay tuned for that. Anyway, thanks for watching in this video and see you in the next one.